Okay, good morning to all of you. In this class, we are going to discuss about transformation of random variables. In our previous class, we have been discussed in detail about chi-square distribution. We proved that PDF of the chi-square distribution. We discussed moment generating function about origin, and with the help of moment generating function we evaluated first and second moment and variance. So in this class we are going to discuss about transformation of random variables. Okay, so let's start. So first of all we are going to go for the one dimensional random variable transformation, then we are going to go for the two dimensional and n dimensional. Here you can see that suppose we have a random variable x defined on a event space S, and we are going to consider gx is a function such that y equal to gx, then this y equal to gx is also a random variable defined on S. So here x is the random variable in the event space S. Then if we are going to consider another random variable which is the function of x, that is your y is also the random variable in the space S. Okay, so in this section mainly we are going to evaluate the probability density or your PDF of a new random variable, that is your y, which is the function of x, y equal to g x or y equal to f of x. You can write here, I written g random variable x, where the probability density function of a random variable x has been given. That means in this section whatever we are going to be discuss, we are going to discuss that already we have the probability density function of x and we have to find out the probability density function of y. Okay, how it will be? That can be done by the theorem. This is the theorem. Here x be a continuous random variable with PDF, that means your probability density function fx, which is the function of x. Let y is the function of gx be strictly monotonic increasing or decreasing function of x. Assume that gx is differentiable and hence continuous. So if gx is differentiable, then obviously it is continuous for all x. The PDF of y, the random variable y, here y is the values of random variable y. Okay, y, small y is represents the values of random variable y, which is the function of g of capital X, or this small y also can be written as g of small x. Okay, here represents y equal to g of capital X, means it is represents the random variable y is the function of random variable x, and here this small y equal to gx, it represents the values of random variable y is the function of values of random variable x. Okay, so this is one to one mapping, only one to one mapping. So either we can write in this format or we can write in this format, no problem. Okay, so here y equal to gx be strictly monotonic, either you are going to consider increasing or decreasing function of x, and gx is differentiable everywhere, and hence if it is differentiable, obviously it will be continuous for all x. Then PDF of random variable y, or PDF f y of the random variable y is given by fyy equal to PDF of x, that means small f x x modulus of dx by dy. Okay, so the random variable PDF of random variable y will be this much, that we are going to be prove here. Okay, here x is expressed in terms of y and the range of y is determined from the given range of variable x. So here obviously if it is one-to-one mapping, um, for each value of x we are going to get 1 y value. So the range of x will be determined the range of y on using the transformation of y equal to gx. Okay, now we are going to go for the proof. First we have to consider case 1 where y equal to gx is a strictly increasing function of x, that is your dy by dx is your positive, that is greater than 0. We have to consider first case, case number 1, and then we are going to go for the second case where dy by dx is a negative, right? That means decreasing function. Okay, now the distribution function, if we are going to consider the distribution function of random variable y is given by, you just recall that we have a random variable, suppose x, the distribution function f x x is nothing but your probability of x, probability of x for all values of x, probability of for all values of x. Okay, that we know. Similarly, if we are going to write distribution function or df of y is given by f of y equal to y, probability of y less than that of the y is equal to, here y is nothing but is your gx. Okay, so instead of y, as we defined that y equal to gx, and here also the values of y equal to the function of values of x, so instead of y can be written as g function of x less than that of the y, right, is equal to probability of, here you can see gx less than equal to y, that means x will be less than equal to g inverse y, right? See, here we consider that this is suppose your variation of x and this is variation of y equal to gx suppose, and we got a increasing function and the graph is something like this. Suppose it is increasing one, suppose the graph is this one. So if the gx graph is this one, then which is continuous and differentiable, then here we can write x equal to g inverse y, right? So as it is each and every point it is differentiable and continuous, then its inverse has to be exist. Okay, so x will be nothing but g inverse y. So here also we can write in general that x equal to less than equal to g inverse y, whatever written over here, right? Here the same is written, the inverse has to be exist, the inverse of g, the inverse of g. Now you just write this one, the inverse has to be exist, that means g inverse y has to be exist and also unique, because gx is strictly increasing function, right? So therefore f of y, this is your distribution function, can be written as, here you can see capital X less than that of this value. As I told that any distribution function can be written in this form. So if instead of x I will write g inverse y, then here this will be written as f of x of g inverse y, right? So same thing it has been written, f of x or the so called distribution function of y is nothing but distribution function of g inverse y. So that implies if distribution function of y will be equal to distribution function of x. Why? Because y equal to gx, therefore g inverse y is nothing but x. So instead of g inverse y we can write x, right? Because if gx is continuous and differentiable at any point, there is no discontinuity. Each and every x we have the y value, then its inverse, that means x equal to g inverse y has to be exist, and also this will be also continuous and differentiable, right? Now we are going to consider the differentiation of equation number 1. This is your equation number 1, whatever we found. Differentiation of equation number 1 with respect to y. What we are going to found? You can see d by dy of distribution function of y is equal to d by dy of distribution function of x. So here the differentiation of distribution function of y with respect to y is nothing but PDF of y, that we know. The probability density function, we know that PDF of any random variable, suppose y, is nothing but f of y is nothing but differentiation with respect to y of its distribution function f y. So if instead of y we are going to consider z, then it will be z d by dz of f z, sir, f z z. Okay, these things already we know. Now here this is nothing but your PDF of y, and here you can see d by dy is there. So d by dy can be written as d by dx into dx by dy. So d by dx of distribution function of x is nothing but PDF probability density function of x into dx by dy. Let this is your equation number 2. Now we are going to go for the case 2. Okay. So before we are going to discuss case 2, here I am going to give a simple idea about your gx less than equal to y, or gx equal to y and x equal to g inverse y. Here you can see, suppose we are going to consider a function like y equal to x square, right? Or we can write y equal to g of x. Okay, so that implies here x is nothing but your root over of y, or y to the power 1 by 2. So here uh, in this way can be written as x equal to g inverse y. So here g inverse represents the square root, and only g is represents the square. Okay, likewise you can consider, suppose y is equal to suppose e to the power x we have. So that means y equal to g of x, that is your e to the power x. So here that implies x equal to log y, and here we can write that g inverse y equal to x. Okay, so here g inverse is represents the log, where g represents the exponential, like this you have to just consider. Okay, so in all way we can say that if gx is a strictly yes, one thing I forgot, that here you can see that if your y equal to x square, this is your x and y equal to x square is a monotonic increases function, Then x equal to y to the power 1 by 2, also a monotonic, but slowly monotonic, also monotonic increasing function. Okay, so hence in all the way we can say that if gx less than or equal to y, uh, x will be less than equal to g inverse y when the gx is strictly increasing function of x. Now we are going to go for the monotonic decreasing function of x where dy by dx is less than 0. So now the distribution function of y in general distribution function of a random variable y is written as f of capital F subscript y function of y, which is written as in general probability of y less than y, right? Now we have been considered that the values of y equal to function of values of x or y is equal to g of x, that we have been considered. So instead of y we can write g of x less than equal to y is equal to probability of x greater than equal to g inverse y, right? Because as here gx is strictly monotonic decreases function, so obviously here x will be greater than that of the g inverse y, right? So this can be written as 1 minus probability of x less than g inverse y. If x greater than g inverse y, probability of x greater than g inverse y we have, this can be written as 1 minus x less than that of the g inverse y, right? So this is nothing but your distribution function of g inverse y. So distribution function of y equal to 1 minus distribution function of g inverse y is equal to 1 minus distribution function of x, because y equal to gx and g inverse x equal to g inverse y equal to x. So g inverse y, instead of g inverse y we can write x. Let this is your equation number 2 and this is your equation number 3. Now we have to differentiate this and this, left side and right side. What we are going to find out? We can find out that fyy is equal to d by dx of this much. Okay, sorry, d by dy, here d by dy of this one. So this d by dy can be written as d by dx into dx by dy, and f of y will be equal to here minus differentiation with 1 it will be 0, and this will be minus d by dx of this one is nothing but density function of x, random variable x. So this will be the small x into dx by dy. So f of y equal to f of x into minus dx by dy. So this negative is represents that x is decreasing function of y, or dx by dy is less than 0. See here dx by dy is less than 0, that means it is negative value, so negative sign automatically came up. How and why? Because if y is strictly decreasing function, here we consider that gx or y is strictly decreasing monotonic decreasing function of x, so obviously x is decreasing function of y, okay, or dx by dy less than that of the 0. So by considering equation number 2 and 4, in general we can write f of y or PDF, probability density function of y will be probability density function of x into dx by dy modulus of dx by dy. Here we have been proved that the PDF of a random variable y, which is the function of x, as like this y equal to gx, or you can say that capital Y equal to g of capital X, then the PDF, probability density function of y, will be the given PDF of x into modulus of dx by dy. We have been proved by considering monotonic increasing and decreasing function. And whatever we have been proved, that also can be proved in this way. Okay, you just put the heading transformation of random variable. Either way we can prove this one, that uh, PDF of y equal to given PDF of x into dx by d modulus of dx by dy. So in this way, how we are going to be prove, you watch carefully. Now let x is a random variable distributed with PDF, this one, small f x, which is the function of x. Now suppose we have another function. We have a you just write another function. Okay, another function y, which is the function of x as g of x, or you can write small y equal to small gx. This is, see, this and this, the physical meaning is same. This is represents the random variable y is the function of random variable x. This represents the values of random variable y is the function of values of random variable x. So here from this it can be perceived that this is a one-to-one mapping. So one-to-one mapping means for each value of x we have y, right? That means there is no discontinuous. So one-to-one mapping means continuous and differentiable. Gx is your continuous and differentiable. Okay. Simply it can be inverted to find x in such that x equal to g inverse y, right? So if gx is a continuous, what we discussed just now, if gx is a continuous and differentiable, then x is nothing but your g inverse y, because its inverse has to be exist because it is differentiable and continuous. Now we intend to find out what is the PDF of y. Let this is your PDF, f of y be the PDF of y. Now here we can evaluate the probability of random variable x in x and x plus dx is how much? If we have the probability density function of x is this much, then in the range x, in the range of x and x plus dx will be, what will the probability? The probability density function into dx, that we know. So now here we can evaluate the probability of random variable x, because already probability density function of x is given in already given. So probability of random variable x in the range x and x plus dx is how much? Probability of x less than equal to capital X the capital X greater than equal to small x less than equal to x plus dx. That means total probability in between the range, that is your x and x plus dx. In between this range, what is the total probability? That is your probability density function into the length. So if one dimensional we are going to be consider, so per unit length, what is the probability? Per unit length, this is the probability, that is it is represents its probability density function. Per unit length, this is the probability. So in this length which is exist in between x and x plus dx, in this length what will be the probability? The probability is your probability per unit length you can say, or you can say probability density function into that length. Okay, but x and y, or you can say small x and y, are one to one mapping. So each value of x, so here we are considering one dimensionally the variable of random variable of x. Okay, so here the variation of x, is along this way. So due one value of x, we are going to get the one value of y, where the y is varying. Suppose this line is the variation of y and this line is the variation of x. So each value of x, one value in the y line. So if we estimated the probability in between the length x into x, in between the length x and x plus dx, and both the random variable x and y are one to one mapping, that means each value of x we have one y value, then the probability in this range, that is your x in between x to x plus dx, or in the length dx, will be equal to the same length. Suppose this is the dx length, and we are going to consider dx equal to dy. Suppose in your y line this much length is your dy length, then left side I have been multiplied for PDF of x will be multiplied with PDF y, because both are one to one mapping, means each value of x one y has to be exist, each value of x one y has to be exist. So as only for that it is written x, it has unique mapping to corresponding y value, then probability in the length dx has to be equal to probability in the length dy. This is nothing but called as your conservation of probability. Okay, conservation law of probability, according to, you can write according to conservation of uh, conservation of probability, according to conservation of probability. That means you just consider, suppose entire x range, suppose 0 to 10 is there, 0 to 10. So for this range, for this continuous range, it has the continuous range of y also we are going to get, that may be 0 to anything, but for this range y has also a range. And if I am going to be integrate f x dx 0 to 10 will be give you the one value, and this, if this y value corresponding to 10 will be anything, and if I am going to integrate 0 to y, fy dy has to be 1. So this, the total probability in the whole range of the x will be give you 1, and total probability will be give you 1. So as x and y as are the one mapping, and the probability in the range dx has to be equal to probability in the range dy, according to so called conservation of probability. Okay, so that implies PDF of y will be f of x into dx by dy. So in general here we have been written dx by dy mod, because sometimes we can found this is monotonic increase or decrease. So instead of dx by dy, in general we have been written dx by dy mod. And here PDF of y we found fx mod of the j, that is nothing but Jacobian. That means here we have been proved our theorem. Here this is our proof of the of our theorem, and dx by dy here it is called as your Jacobian in 1D. Okay, may you remember, and whatever you have been studied in your previous semesters, and we know very well that Jacobian is used to transform from one coordinate to another coordinate system, or it is used to changing the variable, changing the variable. So you just recall that we know that in two-dimensional case, if xy in the Cartesian coordinate system transformed to polar coordinate r theta, the corresponding Jacobian is written as j equal to del xy by del r theta is the matrix of del x by del r, del x by del theta, del y by del y, del y by del r, mistake, del y by del r, del y by del theta. Okay. Similarly, this is r. Okay. Similarly, if we are going to consider xy are the two variables transformed to new variables uv, the Jacobian will be written as j equal to del xy by del uv will be equal to del x by del u and del x by del v, del y by del u, del y by del v. Likewise, if we are going to consider in the three-dimensional xyz transformed to uvw, then Jacobian will be written as del xyz by del uvw, that is your del x by del u, del x by del v, del x by del w. This is the matrix of, okay, del y by del u, del y by del v, del y by del w, del z by del u, del z by del v, del z by del w, that we know. Okay, so here I drawn a simple problem by using Jacobian, that find out the value of 0 to infinity, 0 to infinity e to the minus x square y square dx dy. This is the question in the form of, in the Cartesian coordinate system. We have to transform it to polar coordinate system and we are going to be solve it. Okay. I forgot to say one thing to you, that here you can see that for one-dimensional random variable case, suppose we have x random variable and it is transformed to y as y equal to g of x, and the PDF of y is nothing but your the so-called Jacobian dx by dy, one-dimensional Jacobian into f x PDF of x, modulus of Jacobian, right? So likewise, in case of two-dimensional random variable, suppose we have, and its joint PDF is nothing but is your f of xy equal to xy. This is your joint probability density function for two-dimensional random variable, and it is these two variables has been transformed to another two random variables, suppose u and v, by means u is the function of xy and v is the function of also xy, then PDF of uv will be written as PDF of xy into two-dimensional Jacobian. Okay, two-dimensional Jacobian means here xy has been transformed to uv, that means del of xy by del of uv, or the so-called matrix is your this one. Here this matrix will be nothing but this one. Likewise, for three-dimensional case, suppose we have three random variable and its joint density function is your xyz, and it is transformed to another three variables like this uvw, and corresponding density function for uvw, it will be density function xyz into three-dimensional Jacobian. Three-dimensional Jacobian means this one. Here xyz variable transformed to uvw. That we are going to discuss in detail whenever we are going to discuss the two-dimensional random variable transformation. So here we are going to solve that question with the help of Jacobian, right? So here the above question will be solved by using polar coordinate system. Here you can see that dx dy means in case of Cartesian coordinate system, we have this is along x-axis, along y-axis, and the limit changes from 0 to infinity. 0 to infinity means x changes from 0 to infinity, y also from 0 to infinity. So if we are going to consider a small section, and here this is your the length belongs to suppose r, and this is the theta, so the entire region, see here, x changes from 0 to 1, 0 to infinity. 0 to infinity means it is in the first quadrant itself, first quadrant only. Okay, so here you can see the, if we are going to consider the small this area, suppose this area, then the this length is considered as r, suppose, and this angle suppose theta. So if this will be theta and this is r, this is also r, then its x component will be r cos theta and y component will be r sin theta. So x equal to r cos theta, y equal to r sin theta, and r square obviously, x cos x square plus y square means r square cos square theta plus r square sin square theta. So obviously it will be r square, because sin square theta plus cos square theta will be 1. Now here theta will be vary from, as it is in the first quadrant, so theta will vary from 0 to pi by 2, right? And r will be vary from 0 to infinity, because x varies from 0 to infinity and y also 0 to infinity, so r will vary from 0 to infinity. Okay, in Cartesian coordinate system, the area element, if we are going to consider a small area, suppose this is the small area we are going to consider, then the area element will be is nothing but dx, small dx into dy, right? Small dx into dy in your Cartesian coordinate system, this one. But in case of polar coordinate system, you can see that the polar coordinate system, this length is your dr. Okay, this length is your dr, and this length, if this angle will be d theta, small d theta, then this is equivalent to this length. This length is equivalent to r d theta. See, here we consider from 0 to this much is r. We can consider from here to here distance also r, because r is in general variation of the radius of this half circle. Okay, so here if we are going to consider this length is or r, suppose, so this is the arc. Okay, so this much length will be r d theta, and this much length is your nothing but your dr. This much length is your dr, and this is your r d theta. So in case of polar coordinate system, the area will be how much? As dx into dy is called as your Cartesian coordinate system. In case of Cartesian coordinate system, this is the area element. Likewise, in case of, instead of dx, we can write this is your dx, right? This dx can be written as dr, okay, and dy, that means this much height approximately will be r d theta, right? So here you can see that in case of Cartesian coordinate system, we have the two variables, that is your x and y. So in your integral dx dy is there. So if I will convert this integral to the polar coordinate system, simply dr d theta, dr and d theta, or r theta is the variables in your polar coordinate system. Simply I could not write dr d theta. Okay, because if we are going to consider the area element, this should be area element. That means dx dy represents the area element, so it has to be dimensionally correct. That means if we are going to write dr d theta, so it is not dimensionally correct, because this is your length square and here is only one length. So here actually it has to be multiplied with 1 r. So r dr d theta. So here dx dy is the area element in your Cartesian coordinate system. Something multiplication needed, that we, if you are going to consider dr d theta, and this something is nothing but your Jacobian. So here you can see that if we are going to find out that xy is transformed to r theta, then the Jacobian will nothing but dx by dr, whatever we have been written over here, dx by dr, dx by d theta, dy by dr, dy by d theta. We have to find out, because if we are going to find out here, dx by dr will be nothing but minus, sorry, cos theta only, and dx by d theta will be r cos theta, r sin theta. See here, dx by dr will be cos theta, here I written, and dx by d theta will be minus r sin theta. Likewise, we have to consider del y by del r, your sin theta, del y by del theta will be r cos theta. So if we are going to solve this matrix, so you can see this multiply with this, it will be r cos square theta minus, here is minus is there, so plus r sin square theta. We found r, so here it is the Jacobian. So whenever we are going to transform this small element of area to another coordinate system, so simply we are not going to write the variables. So here in Cartesian coordinate system, x and y variables, but in polar coordinate system, instead of dx dy, we cannot write simply dr d theta. We have to multiply the Jacobian, that is your r. Okay. So here in polar the area will be r dr d theta, nothing but Jacobian into dr d theta. So here Jacobian will be r. So now we are going to solve the integration, that is 0 to infinity e to the power minus x square y square by dx dy. This will be 0 to pi by 2, because if we are going to consider theta, this will be 0 to pi by 2, and x and r will be 0 to infinity e to the power x square plus y square is nothing but r square, and dx dy is nothing but r dr d theta. So with theta, if I am going to integrate, then 0 to pi d theta, so it will be theta, and if we are going to put the limit, so pi by 2 we are going to get, and 0 to infinity r e to the power minus r square dr. So this is a gamma function. Already we have been discussed that gamma function, if it is in this form, right, x to the power n e to the power minus a x to the power m into dx, then it will be 1 by m into 1 by a to the power n plus 1 by m into gamma n plus 1 by m. So if we are going to compare this integral with this integral, here n is your r to the power power of the r, that means n equal to 1. Here coefficient of r square is 1, that means a equal to 1, and r to the power 2 means m equal to 2. Now we have to consider this output, and we are going to get 1 by m. 1 by m means 1 by 2 into 1 by a is 1 to the power n plus 1 by m. N plus 1 means 2 by m, that means 1. So 1 to the power, this is 1. Okay, this is 1 into gamma n plus 1 by m, that means gamma 1. So here we found gamma 1 is nothing but, we know the value is 1. So we found pi by 2, and this is 1 by 2. So pi by 4, this is the answer. Okay, here I done a question by using the Jacobian, how we have to transform one coordinate system to another coordinate system. So here we have to stop our today's class. In our next class, we are going to discuss some numericals about your one-dimensional transformation. Okay, by using one-dimensional transformation method, we have to solve few numericals. Then we are going to go for the two-dimensional transformation. So thank you so much for watching this video. I suggest that you have to watch carefully and write down the note and ready for the next class. Thank you so much. Thank you.